and welcome back to Think 301. We are on session 11 and we are following up on our time value of money. We're going to look at a few more details compared to what we did in our session 10 where we had the introduction. Now, we know that the value of money changes over time due to factors such as inflation and the interest foregone on cash holdings. Now, whilst we have already introduced you to the basic concept of time value of money, we are going to look at how to compute the relevant or the present and future values of multiple cash flows, and where sometimes the cash flows are similar in terms of timing and amount, we're going to look at how they translate into annuities and perpetuities and how these can be valued. So at the end of the session, we want you to be able to understand the concept of annuities and perpetuities, know how to compute the present value of cash flows, that is especially multiple series of cash flows over a period of time. Now, for this session, we expect that you would have a very clear understanding of perpetuities and annuities, look at multiple cash flow discounting, and then how to apply them for investment seasons. In our last session, when we looked at the single cash flow, we're going to look at some extra details. Now, take it for example that you have an investment or an idea or a vacation you would like to take sometime in the future. You know how much it will cost. And then you only have a predefined amount today, and you can also only earn a maximum amount of interest. Now you need to know how long will it take for that money that you have in your account to grow and transform into the amount that is needed for your dream job, holiday or vacation, or your dream car. Now that literally means that you would have to look at how long it will take for you to grow your present amount into the desired future amount. Using the basic concept of the future value construct, what you do is to solve for your t, and that is normally captured by taking the log as you make the relevant change of subject. So in this case, we have a case that taking the log of both sides, for you to be able to grow your 5,000 into 10,000, given an interest rate of 10%, you will have to wait for 7.27 years. So now this is something you can use in your planning for a vacation that you may want to take sometime in the future. Now, in some other cases as well, it is the possibility that you already have a predefined time. You cannot wait indefinitely for your money to grow. So you would have to go around looking for the right rate of investment that will ensure that you will have your goal, given that you also have a fixed amount. So take it that the total cost of sending your child to college when they are in 12 years time will be about 50,000. And all you have is 5,000 to invest today. So what rate of interest must you look for to ensure that you would have the needed 50,000 to fund your child's education 12 years from today? Using the same future value formula, you fill in the relevant values and then you solve for your R. So all that requires is your basic algebra to do your change of subjects, making your R, and at the end of the day, what you have is that you need to earn at least 21.15% if your 5,000 is to grow to 50,000 in 12 years to ensure that you send your child to school. Now, having looked at how long you must wait for a dream to come true, or what rate of interest is enough to grant you a dream or a wish, we need to also now begin to look at another dimension. So far, we have only focused on single cash flow. That is, you have one-time investment and then you wait for it to grow or you discount it backwards once. Now, in the normal scheme of things, we normally have multiple cash flows. So for example, at the end of every month, you put away some money towards a dream that you have. Or at the end of every year, you put away a portion of your bonus or something akin to that. So in essence, we've got multiple cash flows. Now, if the cash flows are not regular, and are not identical in terms of timing or size, then all we have to do is to just look at the individual future values, if it's a future value you're looking at, and then just add the individual future values, and you arrive at your composite future value. On the other hand, if you're looking at present values and they are also not identical in the terms of timing and amount, then you use the present value formula for each of the cash flows, and then you sum up the total to get your composite value in terms of present values. Now, so this is an example where you have an investment that pays 200 1 year from today, and the cash flows will increase by 200 every year through to year 4. So if the interest is 12, let's see what actually happens. So then, a year from today, I get 200, then it goes to 400, another 200 is added, it goes to 600, and then it goes to 800. Now, when I discount them, the present value means the first payment is actually worth 178 in terms of today. 318, 427, and 508. Together, because they have all been now put on one timeline, I can easily now add up. I cannot add what I receive in year 1, year 2, year 3, because they are on different time planes. When I add everything together, I have the true value being 1,432. Now we are told that the issuer is offering this investment for 1,500. What it means is that it's being sold for much more than it is worth, because its true worth is 1,432. For this reason, this investment offer is not good unless it's being sold for 1,432 or less than that value. Now that's for the discounting of multiple cash flows. Now if you have to compound over multiple periods, which is more than once a year, then what really happens is that we're going to divide rates, which are normally quoted per annum, by the frequency of computation of interest, which is the frequency of compounding, and then that gives us, so if let's say M is semi-annual, semi-annual shows that it means that's 2 frequencies in a year. So R divided by 2 gives us the rate for semi-annual. Now T is for number of years typically. So if we've got 2 in terms of frequency referring to semi-annual, it means that I'm going to earn 6% semi-annual interest for 4 years, because I'm going to have 4 periods of 6 months each. So then this becomes how to compute the present value of a facility if interest is compounded more than once a year. And then, so this is what we have the example, semi-annual compounding. So we divide the annual rate by 2, that gives us 6. And since the investment is for 3 years and it's on semi-annual basis compounding, it means we've got 6 periods. That brings us a value of 70. So that is how you include that. Now with that frequency of compounding, therefore, comes a reasonable question. So what is the effective annual rate on such an investment? The higher the frequency, normally, the higher the effective annual rate of interest, because every time we earn interest, and we earn interest on interest, which is the effect of compounding, then it translates into higher returns on investment. So this is what we have. So the interest that will give us the same end of wealth after end of investment wealth after 3 years is what we refer to as the effective annual rate of interest. It means once we apply this interest, we come up with the same thing as would be if we had gone through the procedure. And so that becomes our EAR, and this is it. So even though the interest rate quoted was 12% to start with, effectively 12.36% was at place because of the frequency of compounding that was in excess of once per year. So that's what we have for effective annual rate of interest. So for an EAR, that is effective annual rate of interest for 18% annual rate compounded monthly, it means we've got 18% per annum. We are going to divide it by 12 because the compounding is monthly. That gives us 1.5 in terms of monthly interest rate. Once we apply that, the effective annual rate of that would come down to 19.56. So effective annual rate of interest is quite relevant. Now, when it comes down to further applications, we can look at issues like a perpetuity, a growing perpetuity, we've got an annuity, and we've got a growing annuity. Now, let's start by looking at the root definition, which is the annuity. Annuity usually is a constant stream of cash flows that lasts for a fixed period of time. So, say I have an investment that gives me 100 Ghana cedi every year for the next 5 years. Once it's every year, 100 Ghana cedi, 5 years and ends, we call that an annuity. Now, it so happens that if I'm going to be receiving 100 Ghana every year until God comes, in which case it goes into perpetuity or is perpetual, we call that the perpetuity. So it becomes a constant stream of cash flow that lasts forever. Now, you may have a case where it could actually be a perpetuity, but it grows at a constant rate. So we call that a growing perpetuity. And in the same range, we can have an annuity, which is not going to be for an indefinite period, but for the fixed period of time during which we get it. At every point, the previous amount grows by a constant rate for that fixed number of periods. So we refer to that as what? A growing annuity. And this has a way of being measured. So now let's look at an example. Look at the perpetuity first. Perpetuity means that constant payment that doesn't grow into the indefinite future. Now, when we look at this closely, when we look at the present value of this and it goes on indefinitely, by using what we refer to as the annuity formula, which is given as this, we realize that as the perpetuity is similar to the annuity, the only difference is that t approaches infinity. So as t approaches infinity, this portion of the formula becomes negligible, so small, because as t approaches infinity means this value becomes so huge that 1 divided by this very large value gives us something like 0.0000, negligible amount, which then negates this portion of the formula and gives us c over r, literally times 1, which is what? C over r. So then the perpetuity is just an extension of the annuity formula, except that t approaches infinity. But on the other hand, to value the annuity, you can easily use this formula, in which case then this is through geometric progression that tries to sum up. So if you've got a 10-year annuity, you put in the 10 and then you put in the values and then you solve for it. It's similar to picking them individually and solving for the period, but there's no point in doing repetitive work when you can use this formula. When we have a future value of annuity, what it means is that we are looking for the future value of multiple cash flows that are identical in terms of the payments and the timing. Now, using that, then we're going to have the case of a future value of annuity that is given by the formula that is also computed using the geometric progression of a business, or should I say the geometric progression of the formula or the future value formula. Now, in some cases, we actually would have an unusual formula or a usual case where a 4-year annuity doesn't make its first payment upfront, but it makes it over some period. So what you do is that you may still apply the annuity formula, but then you will roll back, because the annuity formula works on the premise that the first payment is starting 1 period from today. So if you look at this timeline, the payment is not starting 1 period from today, but it's starting 2 periods from today. So when you apply the standard annuity formula, it rolls back the payment to this point, in which case then you need to roll it back one more step to be able to arrive at the present value. So that is one way to which you can apply unto yourself on for unusual cases where the payments do not necessarily follow the right pattern. Now, let's look again once more at the future value concept. Now, the future value for the stream of payments is given as this, so that we have the annuity or the constant payments. If you look closely, this is similar to the future value compounding factor, and so this becomes the future value of annuity. For which reason then the future value of annuity factor is given at this. This is one of the easiest ways to be able to determine the future value of constant payments you would be making over time in relation to a posited investment agenda that you have. Now, this is an example where you have 5,000 that you'll be investing every year for 10 years, and the money is going to be earning 6% per annum. So what do? Put in the 5,000 here in the constant slot. You'll be earning 6% for 10 years, and then you fix that into the formula. It means at the end of 10 years, 5,000 earning 6% will amount to 65,903, and that is quite a substantial amount. So in case you have any vacation you plan to embark on and you want to save periodically towards this, this is one formula that comes quite in hand, or it's handy for computing such needs. So this is another example here. So this is what we have. So then if you got compounding to be more than once in a period, then the same compounding or multiple compounding effect is also just adjusted into the formula, and that gives us the value. So if you look at it closely, what you realize is that the principles are the same, but whether the compounding is more than once a year or beyond, we just make adjustments to the ordinary formula to take care of the other extraordinary issues. Now, what if you've got payments that comes in ahead of time? One thing that I have not fully mentioned is that in the normal course of business, payment is always after the fact, meaning that you work and then you get paid. You work and then you get paid. But in one or two situations, sometimes you pay before you enjoy. And that could be likened to, let's say, rent. When you have to rent a place, sometimes you pay before you use. Now, in that regard, if I am the one receiving rent payment, it means that I do not receive the rent payment from my tenant at the end of the season, but rather at the beginning of the season. If I were to invest that over the period during which a tenant has taken over my property, what is likely to happen is that I'll be investing my money starting from right now instead of starting a year from today. And that intrinsically translates into an improved investment return, and that can be adjusted for by just adding the 1 plus. So the extra period is accounted for by the 1 plus what? The R or the I, and that takes care of the extra period for which the investment has. So your N still reflects the number of periods for which. So if it's a 10-year period, you still do the 10 in the formula, and then you will adjust for the extra period because payment was made in advance. Now, the same principle will hold, therefore, that if you've got payments in advance but you're looking at an ordinary annuity, you're still going to adjust by just multiplying by the 1 plus the I, which takes care of the extra period for which there was no compounding, because if you've got the present value of annuity, what really happens is that this is the formula for the present value of annuity, where you've got the present value of annuity factor multiplied by the annuity value. Now, this is the normal formula where you have to deal with an annuity due and you want the present value. you just have to adjust by the 1 plus I. Now that then makes sure that the payments that was made in advance, for which reason it cannot be discounted. Because let's take for example, if you've got a payment to be made in terms of, let's say, our rent example, it means instead of the first payment coming to me on point 1, which is the normal case for ordinary payments, my first payment will be received immediately before the client takes up my room to use for 1 year. And when they want to use it for the next season, which is year 2, they will pay me at the end of year 1 or at the beginning of year 2. So at any point in time, if you look closely at the timeline which we have already discussed, payment now will not be discounted because it's being received on point 0. Now once that happens, it means that to a large extent your payments will be discounted short of 1 period. So when you use the normal annuity formula, which will still take care of all the number of payments, you do the adjustment by multiplying with the 1 plus I to readjust for the 1 period that did not have to undergo discounting because of the timing of payments. And so this example we have where we have 50,000 paid at the beginning of each year for the next 20 years. And so then, even though it's for 20 years, only 19 of those will actually be discounted. So even after using the ordinary formula, which will account for the 20, you re-multiply by the 7% to account to earn the interest back for the one that you discounted. So that's one way to use the present value of annuity due formula. I believe that should bring us to a significant portion of it where we see the formula. So for the ordinary annuity, this is the formula, and then for the annuity due, we adjust for the 1 period, because if you look at the cash flows, you can see that payment in terms of months, we receive this, and then time annuity due, the payment actually does start on a very different time frame. So then, in terms of the valuation, it is important to always know that annuity dues start earlier than anticipated. So normally they start on point 0, and then in computing that, you have to ensure that you adjust for the timing effects in such. Now the perpetuity, like I mentioned earlier, is just an extension of the annuity. So for that reason, because t approaches infinity, it adjusts the formula to give us C over R. Now, these are things you can keep in mind to help you as you revise. How to determine the future value of a single cash flow, how to determine the present value of single cash flows or series of cash flows, and then based on that you will go on to learn to apply that in determining net present values of investment, how to determine the effective annual rate of interest, what are perpetuities, and what's an annuity. In doing that, do not forget to take a serious look at your reading materials and then to perfect the skills that we have just acquired. Thank you.